My name is Christophe de Dinochin, and today I'm going to talk about a project named DB48X that aims at reviving the spirit of HP calculators, a spirit which I describe as being better than the best. This talk was originally given in Stuttgart during a meeting organized by the Museum of HP Calculators. I record it again in order to have a high-quality presentation. What is the agenda for today? The idea is to show how revering the past is the best way to invent the future. First, I'm going to explain why there is so much HP nostalgia, as exemplified by the Museum of HP Calculators itself. Then I'm going to give a quick overview of the DB48X project. And then I'm going to deep dive in how to build a better user interface, how to deliver better computations, how to build better libraries, notably for user code, or how to offer better performance than what exists today. But first, let's talk about HP nostalgia. Good products make good memories, and HP calculators were known for consistently delivering better than the best performance. As such, they gave us our best memories. So why all the HP nostalgia? Why was I still using my HP 48SX 30 years after I bought it? Let's see a bit through a history of HP calculators. The HP 35 was the first scientific calculators, and because it was electronic and could deliver 10 digits of precision, it was better than the best slide rules that were available at the time. The HP 65, because it could be programmed, was better than the best fixed function calculators. The HP 34C, because it had a solver and numerical integration techniques, could compute things that you did not know how to compute. It could find a solution for you. And as such, it was better than the best explicit calculators, where you had to know the solution yourself. The HP 41C, with this XEQ and alpha keys, would let you access an almost infinite number of features, and it had plenty of expansion ports on the back, and you could connect it to anything. And as such, it was better than the best closed calculators. The HP 15C was tiny, yet completely feature-packed. It had complex numbers, matrix calculations, and so on. And as such, it was better than the best scientific calculators. The HP 28C introduced some form of algebraic expressions and what is known as computer algebra systems. So you could do computations that were symbolic and not just numerical. And as such, it was better than the best numerical calculators. And finally, the HP 48SX, my favorite, was better than the best, and arguably this title is still holding. Okay, let's start with my personal bits of nostalgia, because I was lucky enough to have met both Bill and Dave in person. This is a picture taken while I was working for HP in France, and this is Dave Packard, and the guy behind him, looking at him in awe, that's me when I was younger. And I remember what I was thinking at the time, which was, this guy gave a job to 100,000 people. But I was also pretty much involved into the HP ecosystem at the time. You can see here, for example, a program that I wrote called MuSolver that was published in a book written by Paul Corbis about the internals of the HP 48. And that program would solve a system of equations, of multiple equations. So in a sense, you can see it as the ancestor of the msolve feature inside the HP calculators, like the 48, the HP50G. I also developed a cross compiler that takes time to load. The video is not loading. So I wrote a cross compiler with which I wrote a number of little games, including the lemmings that you see on the screen. So this one I find interesting for two reasons. One is that this video was recorded relatively recently. So this means there are people still playing on these games 30 years after I wrote it. And the second thing is that it runs on the DB48X when I had written the code for the SX initially, and someone else did the porting for me. So you see what you could do with a 4-bit CPU and a little bit of assembly language. That was at the time where the Game Boy was, all the rage because it was brand new. So we were essentially building our own Game Boys out of calculators. What is also interesting about these games is that because the HP48 had an infrared input and output port, which you can see the little arrow at the top above the Hewlett-Packard logo. And so you could exchange programs that way. And this means these programs were exchanged from one student to the next until they reached the United States, and that's how you can still find them on the web today. Now, to be fair, HP was not always going up, up, up. There was a time where there was what I call a downfall of HP, and where HP invent was more a matter of laughing than being taken seriously. Here are some calculators that HP does not need to be proud of, like the Easy Calc 100. I guess it's probably better than nothing. Or the HP6S, which is the 2020 School of Science. Or the HP42, which a number of people really love, but to me that marks the return of RPN, which means that the RPL approach that had been tested since the HP28C was somehow too complicated or something. So it's interesting. This is an interesting model. The HP48G, it's surprising that I would put it there, but the reason I want to talk about it is because it's the invention of model applications, where you had multiple ways to use the calculators that were not communicating with one another, like your calculator is made of various silos. The HP50G was extremely powerful, and it remains the most powerful RPL calculator to date. But at the same time, it's a time where RPL became sort of a shameful hidden feature that you had to enable. And this is marked by the fact that the enter key became tiny. So it doesn't have quite an equal key, but it starts in the algebraic mode. And finally, the HP Prime, which has an absolutely excellent hardware, but where you have to choose between RPN or computer algebra. It's RPN exclusive or computer algebra system. Can't use both at the same time. And it also has tactile only soft keys, which means that you have to look at the screen to know where you put your keys. So you can't do computations fully, like using tactile feedback. Now what changed in large part doesn't depend on HP. It's not HP's fault. It's more like policymakers killed the engineering calculators by imposing rules that forced manufacturers like HP to choose between doing a calculator that was extremely powerful for engineers or doing a calculator that students could use in a safe way, meaning that the calculator should not be upgradable. You could not change the firmware or improve it or upgrade or whatever, because that would allow, in the mind of the lawmaker, that would enable cheating. So when HP was forced to choose between doing calculators for students or doing calculators for engineers, well, they chose students because that's where the market was. But instead of developing for engineers using money from students, they ended up developing only for students. And so after that, HP began milking the cash cow capitalizing on nostalgia, which beats excellence from a number crunching point of view. And that's manifesting as HP replaying the same old cards again and again and again. So they kept the exact same old designs, but then you can ask, is this still better than the best if you're doing the same thing 20 years on? Now, third parties came to the rescue, going well beyond decade-old hardware. There were simulators, notably on smartphones. What you have there on the screen is simply the simulators that I have on my own smartphone. And you see that you can have anything from the HP41 to the HP15C, to the HP48, various models, HP50, HP's, that's the 67 or 70. So you have a wide range of choices. In terms of hardware, there was a recreation by various third parties of classic designs. Swiss Micros, for instance, has done this for the 41, for the 11, for the HP15, for the HP16. That's another implementation of 15 not by Swiss Micros. The M32 is HP42, HP32, HP41. But being able to innovate in terms of hardware meant that folks went a bit beyond what the original HP hardware could do, and that includes having, for instance, larger keys or high-resolution graphic screens, like this one, so you could show more stuff on the screen. In software too, or in firmware, folks started going beyond what HP did. And I have various examples there from firmware running on HP calculators like new RPA there, or emulating existing calculators but going further, like we had 342 that started as an emulator of the HP42 but then went way beyond. That's 342 here. And then we have efforts like WP43 running here on a DM42, or we have WP34S that runs on HP calculators. Now the problem is that one step further generally does not mean that you're doing a giant leap. So this means that the spirit of better than the best became honestly quite hard to find. There is a bit of innovation, and you see here the C47 or WP43 project doing very innovative use of high-resolution screens in order to show curves along with relevant information. But this kind of innovation has become a rarity rather than the norm. So what is DB48X? Simply put, the objective is to deliver the best scientific calculator in the world today. To do that, it starts by reviving Hewlett-Packard's reverse Polish Lisp, the language that was used in HP calculators such as the HP28C, HP28Ace, and HP48SX and following. Now the spirit of DB48X is to do more like the HP48SX than the following machines in a way that I'm going to explain. And the idea is to run that on modern hardware, such as machines from Swiss Micros, like the DM42 or DM32, or even your iPhone. Let me give you a quick primer on the project. The goal is to reinvent the best calculators in the world. So it's designed for the DM32 and DM42, which today are really nice hardware. It's a nice platform to start with. The specifications for the project is the HP manuals with an S. There are many of them, and they don't all say the same thing because the various iterations of HP calculators do not do things exactly the same way. It implements reverse Polish Lisp or ROM programming language. There are various meanings to the acronym, which is this neat programming language designed specifically for calculators that lets you do very, very advanced things in a tiny form factor. So this means you have command line. You can type arbitrary commands, much in the same way as the HP41 had execute, where you could execute any arbitrary command. RPL went a step further, where you can type practically anything, like numbers, etc., and edit them directly on the command line. RPL is known for having many data types that you can see on the stack here, where you have complex numbers and integers and anything. And the DB48X implementation has many enhancements over the HP implementation, which I'm going to talk about along this talk. Now, when I say better than the best, better than which best? Who sets the benchmark in terms of calculators today? To me, the HP48SX is the best RPL experience, and that is still holding after 30 years. By that I mean that it was consistently RPL, not switching between various modes with menus of different kinds and forms and applications and specific sub-applications. In terms of pure feature set, the HP50G though is way beyond. So it has the best RPL feature set, and that includes system level access. It had an internal assembler and things like that. The HP Prime delivers the best graphics with beautiful color 3D graphics, and also, in my opinion, the nicest keyboard, notably in terms of intelligently designed layouts with different colors that let you quickly identify each area of the keyboard and so on. There are some external projects that are inspiration as well, like GNU RPL, that showed that you could do variable precision decimal on the calculators, and also showed how important it was to have a built-in help system. In terms of hardware, the DM42 delivers some of the best form factor you can think of. It's really slim, small, it's very power efficient, runs on a tiny CR2032 battery, and it's also using standard connectors to connect, to have USB connections and present the content of the calculator as a disk to your PC or your Mac, which means that you can upgrade the firmware, you can upgrade the help content, and so on. In terms of research and looking forward, the WP43 and C47 projects are probably some of the best around right now. They have a very large number of really interesting ideas, like the number formatting that you can see on the screen, or the use of the menus with 3 rows of the menus, and so on. So the idea is to embrace the best of each of these projects and reject what is really ungood. So for instance, the weight on the HP48, or algebraic mode on the HP50, or apps on the HP Prime, or the DM42 having ABCDEF as a menu, or the WP43 being slow when it solves. Let's first start with the better user interface. How do we make the calculator easier and faster to use? Let me start with user interface design principles. As you can see in the top right, you have the Macintosh Human Interface Guidelines. And this was a consistent way to present complicated things in a simple way. So how do we make a complicated beast like a scientific calculator usable? First, I want to avoid siloed modes, subsystems or apps. That's something I already said. What was nice about the HP48SX is that all the features were available all the time. You did not have to switch between how to graph in 3D, and then you could not use that to do something with a computer algebra system. It doesn't mean that you do not build on top of it applications. It means that the underlying engine is the same for all your applications, and so they can communicate with one another. It also means being as consistent as possible across features. And I illustrate that on the screen you see on the right with a multiplication sign. When you multiply 2 by 3, you get 6. That's a multiplication of numbers. If you multiply A by 3, then you have a symbolic computation. If you multiply the text A by 3, then you repeat the text A 3 times. And if you multiply a vector by 3, then you have the numerical values in the vector multiplied. So you don't need to think about how to use, which version of multiply to use. It just picks the right one for you automatically. It's also very important to make it easy and safe to explore and discover features. On the HP Macintosh, this was illustrated by how you explore a menu without clicking on menu entries. So this means you could see which features were there without actually using them. But you could explore your menus and say, oh, my application can do this and that and that. In the case of DB48X, this is notably the case with a catalog that lets you see all the features that are available by typing part of the name. It's also very important to focus on efficiency for common use cases. And for that, I illustrate that with this tool key here. That is a sort of smart key that tries to find what you want to do based on what's currently on the stack. It's also essential to provide a detailed interactive reference manual directly inside the calculator, because you don't want to have to grab some external book and search through it in order to know how this or that function works and what arguments it takes and so on. So let's start with data entry. And we're going to see that there are a number of interesting innovations in DB48X, such as smart spacing, smart state, smart angles, and so on. So smart spacing, when you enter numbers, you can see there that I'm entering a fairly large decimal number, then the system knows how to insert spacing on your command line. That was one of the very first user requests on the project of someone saying, the HP17, I think, was doing that. And why can't you do that on an RPL calculator? And it's more complicated on RPL because you have this command line, so you have to insert the spacing as you go along. But now that it's done, it really looks neat. Another feature from other older HP calculators was the ability to enter GMS values, so degree, minutes, and seconds. And so you can see that simply by typing with the dot key multiple times, you can enter numbers like this, and you can do computations on time or angles that way. Another idea about data entry is for hexadecimal numbers. When you enter an hexadecimal number, the first row of keys that has labels A, B, C, D, etc. will automatically enter the corresponding letters because you're supposed to type a number. And you don't need to shift or alpha or enter anything special to get these letters. Just the fact that you indicated with a hash sign that you're entering a base number, and that's enough for the system to know that it needs to give you A, B, C, D, E, F. Entering algebraic expression is also a staple of RPL over earlier RPN calculators. And so there is this expression object, which is delimited by these single quotes that you see on the command line. And so when you enter algebraic expressions in DB48X, you use the key that is on the top right next to the F label. And you see that it has a tick and parenthesis because it plays a dual role. The first time you hit it, it's going to insert ticks so that you can evaluate an expression. But if you use it again, then it's going to insert parentheses instead. Because inside an expression, that's what you need. Text entry also has some interesting shortcuts. Text is somewhat important in RPL, and so there are a number of text entry modes like uppercase, lowercase, etc. And you can use that, for instance, to name your variables or to enter text like this with ABC. With the double quotes on the side, so that represents some text. With a single quote, that's an expression. With a double quote, that's text. There is something called transient alpha mode. So this one is, I showed in an interactive way during the Stuttgart meeting. It's a bit harder to explain just on a video, but the idea is that since alphabetic characters are so often used, it should be very easy to enter them. And so if you hold the left key for a short period of time and immediately after that you type, for instance, A while holding the left key, then you get an uppercase A. If you hold the right key and immediately after that you type A, or the key that has the tool and A on the side, then you get a lowercase a. And this means you can enter text that way pretty quickly without needing to enter a specific alpha mode. You can of course enter alpha mode as well, but this is a sort of modeless way to enter text. That's the transient alpha mode. There is also a very useful feature which is command completion. That was vaguely inspired by the new RPL project, and so when you start typing text and then you hit plus, it enables the catalog. You can also use Shift plus to explicitly call the catalog feature. And in that case, the system is going to monitor what you're typing and provide completions with the menu, the soft keys in the menu. So if you type HEL, you get help and so on. Now, what is interesting is that it first shows the commands that begin with what you typed and then all the commands that actually contain it. And so that lets you find things that you see here with duplicate, where you have features that contain dupe and that do not begin with it. A similar completion system exists for characters. And so there are character menus that you can find with the right shift with 2, that's char, and that lets you access a variety of per language characters. And what is interesting is that for some of these languages, like at the moment it's Greek and Cyrillic, the primary characters in alphabetic mode are going to be transliterated. So that means that if you type A, you don't get an A but an alpha if you're in Greek mode. There is also a complete character catalog, which means that if you enable the catalog feature while you're typing text, it will give you all the variants that look close to the character that you're typing. So if you have an A, you will get the accented A. If you type F, you can have anything like various kind of phi and so on. Now that feature is extremely useful, but I need to find a way to name things, because sometimes it's hard to tell whether something that looks like an A is actually an alpha or a Cyrillic A and so on. So at some point I'm likely to add some indication on screen that tells you, oh, you chose this or that character variant. Now, as you see, we have an extensive use of menus and soft keys, and something that was inspired, I believe, by the WP43 project was the use of these soft keys along with a shift key to deliver up to 18 functions. An innovation that is specific to DB48X is how we deal with the lack of next key. And the reason is because the HP42 and therefore the DM42 has a much lower number of keys than the HP48. So we need to find room and to find tricks to do things with a smaller number of keys. So in the case of function keys, that means that the next key appears directly in the menu. If you have more than 18 entries, you get a little row that appears on the right that gives you next and previous pages. But to get started, you start with 18 functions that are directly visible on the screen. The row at the bottom you get directly, and then you shift or shift twice to get the next rows. When you have a little angle on the side of a soft key, that means it's actually another menu. It's a folder of menu, except that they can interconnect in practically any way. And as I mentioned, you have these next and previous on the right that you can see here, so you can have multiple pages inside a given menu. The tool menu is the top left key, the one next to A, and what it does is select the menu that corresponds to the object on the stack. So this means if you have a real number, you get a real menu. If you have a vector, you get a vector menu, a matrix menu, a text menu, a list menu, and so on. And so this means that with a very short key press that is placed in the corner of a keyboard, so it's easy to tactically feel where it is, you can find your A key without looking, and that gives you a quick access to the features for the whatever is on the stack. The variable menu, or var, will give you access to the variables that are stored in your current directory, and let you evaluate them, recode them, that's the little arrow on the right, or store them if you shift twice with the little arrow on the left. And so that lets you very quickly evaluate a program, recall it to edit it, or store into it. And you see there that I'm storing a value in T, and then recalling it, evaluating it, and so on. Now if you hit var twice, then you have the feature that is called CST, or that's a custom menu on the HP48. And that's a menu where you put essentially whatever you want. So here there is a shortcut for demos, there is something that prints hello, there is an entry that refers to the authors in the help file, and so on. So var once gives you the variable menu, var gives you the custom menu. Now the menus are recorded in an 8-level menu history that records each menu only once. So if you return to a menu where you went before in the past 8, it's recorded in its last position. And then you have this back menu, that's Shift A, and that gives you back, that gets you back to the menus you came from. So again, this is to help exploring. Now, the DB48X project provides a complete and extensive interactive reference manual to make it easier to understand the rather complicated stuff inside. The first thing is that if you hold a key, you get some detailed help for that function. So in the example here, if you hold sign, then you get to the sign explanation. And if you look into the equation catalog and you hold a given equation, the key for a given equation, that's the function key that will invoke that equation, then you get all the details that are normally found in the HP50G Advanced Reference Manual. The point here is that this is a reference manual, not just some quick help. Now, when you have object on the stack, the help feature, which you can access with Shift plus, explains the object on the stack and lets you do operation on it. You can also ask for help on any particular topic by putting the name of that topic on the stack, like 2UNIT here, and it will find it irrespective of how, there may be multiple spellings, but it's going to find it. The help is hyperlinked and has a history, so you can follow a link and then hit the back topic, that's the F6 key. You can also use the backspace key for the same thing, and you go back to where you came from. So here I go to RPL, read the introduction to RPL, back topic, and then back to where I came from. It also recognizes external hyperlinks, though obviously it cannot access the HTTP links because there is no access to the internet on the physical calculator. The help actually contains graphical illustrations. The example here is with the pi function, constant, that explains what that constant means. And it also contains testable sample code. So you have text like this in gray. When you hit it, it's copied on the command line, and you can evaluate it, modify it to see what it does, and experiment with it. That help is written using a language called Markdown, which is the language used to display things on GitHub. So the majority of projects on GitHub use Markdown for their documentation. And so because it's the same language being used for both, this means that all the online help is also available online on GitHub directly on the project website. In terms of daily use of the calculator, how you edit objects is extremely important. So the idea is to make it easy to edit any type of object quite efficiently. First, there is a command line history that you see here that lets you go back into the previous commands that you typed, and you access this with the hist, so second shift and then the left arrow, and you see the blue hist just below enter, and that enters the history. And then the edit menu also has hist up and down features, but as a shortcut, the word left and word right let you also walk through history when you're at the end or the beginning of the command line. The calculator supports a variety of RPL styles, meaning that you can show commands in a way that is either with a long spelling, which is the default, or with a shorter spelling that is reminiscent of the HP48 or HP50. And the shorter spelling can be uppercase, lowercase, or capitalized. So you choose it the way you prefer. What is interesting is that this is integrated in the online help as well, meaning that when you select a given mode, then the help will actually follow that mode and show you the alternate spellings on the right. So there I'm using the long mode, and if I'm using the short mode lowercase, then that's what the help shows. There is a quick navigation and search in the edit menu. The edit menu you reach with shift the right arrow, and you see the blue menu edit. And that offers things like moving one word at a time, moving to the beginning or end of the buffer, but also a search feature that where the cursor will show as, or the selection will show up as gray. It's an incremental search, so as you keep typing things, it moves forward to the thing that contains what you searched. And there is a cursor swap select feature just above select on the F1 key that lets you change the direction. So it swaps the cursor and the selection, and so that changes the direction of the search. So you can search backward by using that. There is also the traditional selection and copy paste. So you hit select and then you select some text. You can cut it, paste it, and paste it at some other place. So it's very familiar to anyone who used a computer built in the last 30 years. Just like there is a transient alpha mode, the same technique applies to F1 through F6, the function keys at the top, to give you the features of the edit menu, even if you're using another menu. So this means once you remember that transient F1, for instance, is for select, you can start selecting text without having to be in the edit menu. And the same thing with search and so on. So the first two menus, the first two rows of the edit menu can be accessed through using the right and left key respectively. The HP48 introduced an interactive stack where you could see objects anywhere on the stack and go back up as deep as you want, edit them, and so on. So the same feature exists in DB48X, though it is quite enhanced compared to the original. You see the 3 rows of menu that you have there where you can echo, show an object, edit it. You can sort objects on the stack up to the level that you selected there. You can roll up and down, you can swap and do all sorts of things. Another very important feature of DB48X that mimics what was done in RPL is how you edit expressions. So RPL supports a complete algebraic expression parser, and this means you can type your expressions, but you can also edit your RPL expressions using RPN. It is something that is sorely lacking, for instance, on the HP Prime. When I say that the CAS and RPN modes don't talk to one another, that's an example of thing you cannot do with an HP Prime very easily. which is, you have an expression on the stack and you add one by using, in RPL mode, 1 plus. While we are talking about editing expressions, so I mentioned that the tick key was somewhat magical in the sense that it inserts parentheses depending on whether you're inside an expression or not. The space, or the key that is to the left of the plus key at the bottom of the keyboard, has a multiplicity of rows depending on where you are. You see that it's labeled as evaluate, space, or equal. And so when you're inside an expression, it gives you an equal sign. If you're inside parentheses, though, it gives you semicolons because you want, presumably, to separate parameters to a function with a multiplicity of parameters. And when you're typing regular RPL, then it inserts a space, which you don't need inside the expression, so that's why it doesn't do that inside expressions. So, and finally, when you're using it and there is nothing on the command line, then it means evaluate what you have. So it's essentially run what you have. This is a muscle memory for HP42 users who have the run stop key at this place. So evaluate is more or less the RPL equivalent of run stop. A new feature on DB48X, which I think is somewhat unique to that calculator, is the cycle feature. So on regular HP calculators, when there is nothing on the command line and you type EEX or E, you get 1E something and you can enter an exponent. Now I thought that was not super useful, so while this E key does the same thing if you enter a number, it also plays other roles in other contexts. So for instance, if you have a numerical value on the stack, it's going to cycle through various forms of that value. So there I'm entering an exponent, but here cycle is converting between fraction and decimal representation of that same number. And if I'm typing a complex number, it alternates between polar and rectangular forms for that number. For a vector, it turns it into vector array list. For a unit, it will let you enter a variety of sizes for that unit very quickly. So you can enter kilometers that way. And if you have a unit on the stack, it's going to cycle between the various sizes or representations of that same unit. Now, you can have a special cycle section in your unit file that defines specific conversions between units that you use often. For instance, if you were converting between euros and dollars very often, you can put a cycle between euros and dollars. And then in that case, the cycle key, when it sees a unit as euros, is going to convert to dollars and conversely. Okay, the next step is better computations. The first role of a calculator is to calculate. And ideally, we want to do that with speed, precision, and accuracy. So I'm using as an illustration for this section la salle Pi, the Pi room in the Palais de la Découverte in Paris. And what is interesting is that when this room was initially built, it had the largest number of decimals, the largest suite of decimals for pi that was known at the time, but only, I think it was about 700 of them, and only about 400 were correct, because the mathematicians who did the calculation made a tiny mistake somewhere in the middle, and after that all the decimals were wrong. So this was fixed since then, which I find shameful. I think I would have left that in the original state. But of course, the idea with a calculator is that you don't want it to do numerical mistakes, or to let you do them. So what are design principles for computations? Just like we discussed design principles first for user interface, same thing for computations. Well, the core idea there is to automatically pick up the right tool for the job. So one example of that is that whenever possible, we want to do exact mathematical computations, even if that means going through various hoops to do that. we also want to be able to compute with the right precision. And the illustration that you have on the right is the infamous Sinclair scientific calculator, which would compute. So it was built, in fairness, it was built using a chip that was designed for 4 operation calculators, and they managed to turn that into a scientific calculator, which was quite a feat. But the cost that you would pay for that is that it was very imprecise and would give you at best 5 digits of precision. Now, because it's built on RPL, DB48X lets you have not just numerical but also symbolic computations. And another important principle is to have smooth integration between the features and consistent behaviors across different tools, but also different variations of the same tools. I'm going to show that in a moment. One derivative of that idea is that we want to avoid computation modes and replace them with object types. An example we already saw is that whereas the HP48 has a mode to select between polar and rectangular display of complex numbers, knowing that internally they are always stored as rectangular numbers, but they can be displayed in polar mode. In the case of DB48X, there are 2 representations for complex numbers. One is polar, the other is rectangular, and so you can have both on the stack at the same time, and you can use the one that is more optimal for the computation you do. Just like, depending on the case, you may want to pick up your Ferrari or your truck. Or it's not a Ferrari, sorry, it's a race. It's a Corvette, I don't know what it is. Another important thing is to treat Algebraic and RPN as equal partners. And HP has been relatively bad in that respect, where historical calculators would favor RPN because it was simpler to implement initially. And then when they switch to Algebraic, you end up with calculators like the HP Prime, where RPN becomes a second, it's like an afterthought. You know, we do that for the nostalgic people among you, but we don't really care. And if some of the features are not available in RPN mode, that's okay. That started earlier than the HP Prime. It was already somewhere there in the HP50G, where some features work much better in Algebraic than in RPL. So in our case, we want to be pure RPL. We don't want to have any assistant, no app. What you see on the right is Microsoft Bob, which is exactly the way we don't want to do things. So how do we do exact computations if possible? As I mentioned, one trick to use is to have various data types, some of which support exact results. For example, DB48X has true integers, big and small. You see the difference here between an integer and a decimal number, where in one case you have a dot and in the other case you don't have it. And integers can be really big, like we have factorial of 100 there, and you see it's a number that takes 68 bytes in memory, but it's completely transparent to you. And if I divide that by the factorial of 97, I can see that the remainder is exact. I did not lose any precision. Decimal numbers take a bit more space. So here, for instance, a decimal 9 is 5 bytes, a decimal 2 is 2 bytes in memory. So you have a real difference between the object types. In order to show what is inside the object, I'm using an interesting feature of the interactive stack, which is info, and that gives you the object type, its size, and a checksum for that object. DB48X also has true fractions. For instance, if you divide 2 dots by 3, you get 0.666667. But if you divide 2 by 3, you get 2/3. And so that's a true fraction. And we can display the fractions as either mixed fractions with an integral part and then a fractional part, or as true fractions with so that one is a mode. That's not two different types of fractions. It's the same numerical representation. It's a display mode, like the number of digits you display. Internally, we also store angles as fraction of pi, which means that we can do exact computations on some particular angles. Like for instance, we can convert 30 degrees exactly to grad, and as long as we don't invoke radians where we have to convert with a value of pi that is not completely precise, but for all other conversions we can do them exactly as long as the value can be represented as a fraction of a half term. Complex numbers can also contain integers, for instance, as arguments, or for the angle for polar numbers, meaning that we can do exact computations on complex numbers as well. And the same holds for vector and matrices. Here, if I divide a vector by 5, I get fractions inside my vector, and so those are exact fractions. Now, why does it matter? Let me take this matrix here. If I invert it, or if I take the determinant, I get exactly 0. Now, this is important because the DB48X, for instance, despite being my favorite, gets that wrong and gives you a non-zero determinant and thinks that you can invert that specific matrix. Expressions also allow us to do exact computations, and you see some examples there where we can, for instance, take the sine of the arcsine of x, and it will automatically remove or simplify the expression as you're doing operation. Same thing if you add one or remove and then remove one, you get the original value and so on. So there are some simplifications like this, and you can control whether the calculator does that. There is a flag that lets you control whether auto-simplification occurs or not, but it makes for much simpler results in many cases. Now, if you can't compute exactly, the next best thing is to compute with the right precision. And for that, we have 3 different choices. One is variable precision decimal, and then we have 2 implementations of hardware, IEEE 754, which is the standard floating point representation. So first, let's start with the variable precision decimal, which is the default, and it by default it selects 24 digits and a maximum exponent of 2 to the power 61. Now you can select the maximum exponent to 499 and the number of digits to 12, and then you get almost exactly what the DB48X and similar calculators will do. So there is a way to restrict the maximum exponent, for instance. But by default, you can deal with really large numbers, with a very large number of decimals. The show feature, which is actually called view on the DB48, show is the name that is used on the DB42, for instance. That will let you see all the decimals in the number, including when you restrict the number of decimals shown on screen, like with the use of the fixed feature and so on. Now, these decimal numbers are stored with variable precision, and that's per value. So each value on the stack can have a different precision depending on, in other words, the precision only affects the computations, not the numbers that are already stored somewhere on the stack. So here, for instance, I'm computing pi using arctangent of 1 and multiplying by 4. I'm computing pi to first 200 decimals and then pi with 20 decimals. And you can see that you don't get the same results, but at the same time, each of the results has kept its precision. So 200 decimals here, same thing for square root of 2. So that's arctangent of 1 times 4, and you see all the digits with show and all the digits on screen. But then if I restrict the number of digits showed to 20 and the computation precision to 20 and do the same computation, now I have 2 versions of pi, one of them with a high precision, the other with a lower precision. Now, decimal is very nice because it lets you do the computations in decimal without too many rounding problems. But most computers use a binary representation called IEEE 754, and the standard for 32 and 64 bits are implemented in DB48X. One of the benefits is that they are hardware accelerated on many of the supported platforms. The downside is that because it's a binary format, it cannot represent things that are not powers of 2 compared to 1 exactly. So for instance, 0.2, which is 1 divided by 5, and 5 is not a power of 2, cannot be represented exactly. And so if you show more digits, you're going to see that 0.2 is really stored as something that is not exactly 0.2. The benefit is that then you are doing exactly the same computations as your desktop computer, and also you're doing them faster than with a variable precision implementation. Like all HP calculators, DB48X has a variety of display modes, like the fixed mode that displays a fixed number of digits after the decimal separator, the engineering mode, the scientific mode that displays a fixed number of digits after a separator and always uses a power of 10, an exponent to show the magnitude of the value. And then an engineering mode, which is the same thing, but the magnitude has to be a power of 3. So these are the 3 modes that also exist on all HP calculators for the longest time. A new mode that I believe was inspired by DB43 is the significant digits mode. And what this does is that it's more or less like SIG, but it doesn't display like fix, but doesn't display the trailing zeros. So this means that SIG12 is essentially gives you a display that is essentially the same thing as the standard mode of the HP48, despite the fact that the values internally might be stored as 24 digits. So you can have 24 digits of precision with only 12 digits for the display. There are other more advanced display controls, like for instance you can select where the calculator switches to scientific mode, and that's with the exp feature here, where you can select the number of digits before you switch to scientific mode. And you have the dig mode that lets you select the number of significant digits. And then you can have all sorts of choices for separators. You can use underscore, you can use spacing, you can use a comma as a decimal separator or a dot, and so on. So all these features work exactly the same, whether on the display or when you're typing in the editor and so on. Now, I mentioned that I want to have Algebraic be on equal footing with RPL. And so the idea is to have Algebraic behave the RPL way, with a single user interface that works both for reverse Polish data entry and for algebraic data entry. So we have first-class algebraic objects, and you simply put a tick around an object, and then you enter your expression like you would on a good old Texas Instrument TI-58 or whatever, except that you see the expression show up on the screen. It's also very reminiscent of what you have on modern Casio calculators, for instance. Now, RPN applies to algebraic. So for instance, I can type x, 1 plus, and multiply by 3, and do that in RPL, and that builds an expression that shows graphically on screen. Now, that is extremely useful to enter complex expressions quickly without getting it wrong. And it's something that, in my opinion, is sorely missing from notably the HP Prime. That's one of the reasons that makes the HP Prime hard to use for me. If there is a way to do that on the HP Prime, please let me know. In terms of equations, so equations are like expressions with an equal sign as the main operation in the middle. And what is special with equations is that when you do an operation, it applies on both sides of the equation. You have complex numbers and matrices that you can enter in algebraic mode as well. And for instance, here I can compute I do symbolic operations on complex number or matrices, like inverting a 2x2 matrix in symbolic form. Another interesting feature is that you can take an algebraic object and turn it automatically to an RPL object you go to the object menu and you use the convert to program feature. And it's actually a fairly cheap operation because internally that's how expressions are really represented. And the reason they are represented that way is so that they evaluate efficiently. The idea is that it takes less time to reorder it and compile it into the RPL operation than it takes to evaluate it. So you pass once, but then each time you evaluate, you can evaluate it quickly. Plotting is also based on taking an object on the stack of algebraic form and drawing. So later there will probably be a full-featured plotting, let's call that application, though it will be RPL integrated, that looks a bit closer to what the HP48 does, like where you have the ability to move a cursor on the screen and get some information about the function being plotted and so on. But for now, the main plotting features will let you draw a function directly on the screen by tapping it on the stack and then hitting the correct plotting function. The same idea applies to solving equations, numerical solver. So you have a root feature that will let you solve a complicated equation, and you can do that both in RPL, which I just showed, and in algebraic mode. Now, the algebraic mode is one of the cases where the HP50G, for instance, does better in algebraic mode than in RPL, because you can actually enter a root with an expression in algebraic mode. You cannot do that in RPL mode on the HP50. So that's one area where the DB48X does better than the HP50. You also have derivative and primitive syntax. So you can say, I want to differentiate relative to x to get a partial derivative relative to x, or a primitive for that x. So there I'm using the algebraic syntax for entering d over dx. So I showed the same thing both in algebraic and primitive, and I'm doing the primitive there first in RPL mode, and then I'm doing the same thing now in algebraic mode, so putting primitive versus x at the beginning, and I have my primitive, and when I evaluate that, I get the value. The third section is better libraries. How do we provide easy access to a large number of predefined things that are represented using standard RPL objects so that users can actually extend the libraries that are built in? Same idea as before. What are design principles for libraries? Well, standard RPL objects and user configurable. These are the two key topics. Library objects are new types of objects. So what you see on the right is the Catalogue d'Objets Introuvables. It's a book by Karelman which shows all sorts of really weird objects, where we have this new type of object for equations, for constants, and for library items. For constants, this means we have up-to-date constants, and that's not only very important for physical ones. The HP50G has some value of constants that since then have been significantly upgraded. And since DB48X is a free software project, this means the source code is available to everyone. So it's fairly easy to follow where the code data latest drop is and put the correct numerical value for a constant after, for instance, we need a new physical measurement. There is a fairly large number of common equations in an equation library that works relatively close to how it works on the HP50G with various improvements. And then you can have user programs. So this is an example of one that is featured in the demos as well as in the standard library that ships with the project, and that compares relativistic and classical kinetic energy. The curve that you see there is wrong because it turns out that when this snapshot was made, there was a missing SQRT somewhere in square root, somewhere in the computation of the relativistic kinetic energy. All these can be extended the same way by using CSV files. So you have a config subdirectory on your calculator, and inside this config you have, for instance, equations.csv, or this one that you see here is units.csv. So CSV stands for comma separated value, and it's something that typically it's a standard input and output format for spreadsheets like Excel, etc. And so in the case of the units, you have the various units menus, like quick, money, and this special equals cycle. It's not a menu, that's the one we use for the cycle feature, something I mentioned earlier. And then you see that there are definitions here where there is a specific definition of inch, just in case you wanted to redefine inch to be something else. Then there is a definition of millimeters. The equal sign on the right means that it will use the standard unit engine to evaluate the mm text. In that case, saying m is a SI prefix for milli, and the second m is meter. And so it's going to evaluate that to 1/1000th of a meter automatically. And so equal just lets you get that for free. Same thing with kilometers per hour. So it's going to automatically look up kilometer, divide by hour, and you get your kilometer per hour for free. Now, what makes it interesting, the fact that you can extend it, means that you can have a valid use of the unit system for money, like for you have US dollar as a reference, and then you write other monetary units relative to the US dollar, and then you can automatically convert between euros and British pounds with the turn of a key. The cycle section in this file is what lets the cycle feature on units detect specific cycles that you care about. And I mentioned, for instance, that you can have a cycle between US dollar, euros, Swiss francs, and back to US dollars. And you would cycle that way between these three monetary units if that's what you use on a daily basis. So why is it cool to integrate that with the unit system in the DB48X RPL engine? It means that you can, for instance, convert between US dollars per mile to euros per kilometer. And the conversion system is going to do all the adjustments for you automatically. DB48X is also using standard Unicode encoding for all numbers, all text, and that means, well, internally it's stored as something known as UTF-8. What this means is that you can copy-paste text from your standard text editor to a file that will be stored on the calculator, and you can read it back, including with accents and all the fancy characters like alphabetic Greek or Cyrillic characters. Now, the subset of characters that are supported include all the Latin and Cyrillic and Greek, mathematical, and so on. It doesn't include, for instance, Chinese or Arabic characters at the moment, and it's mostly by lack of space. We don't have enough memory in the calculator to be able to deal with the largest character sets. And something that I'm working on right now is key maps, another kind of configuration that will let you redefine the default keyboard. What you see here is my thinking for the next generation or next iteration of the keyboard mapping. It differs from what exists today, and notably on the first row where you have the power y to the power of x that becomes a primary function. Right now it's shifted. It takes the place of exponential, that becomes a shifted function, and that's like on the HP48. And the math becomes a primary function as well, instead of being relegated to a second layer menu. So it becomes unshifted, and the feature that was there was the logarithm, and the log becomes a shifted feature. Now, because this is really something that impacts your productivity and depends a lot on preferences, I won't actually ship something with a mapping like this before I give you a choice to revert to an HP42 compatible keyboard mapping or to the previous mapping, because folks who have purchased a keyboard overlay already may not be too happy if I change the keys all the time, and so they will have a configuration that lets them have a keyboard layout that matches the keyboard overlay that they purchased. Now, a big part of the library is the equation library, and the idea there is to leverage something called the multiple equation solver, which is a standard feature on the HP48. I think it started with the GX, and then it went on with the HP50G. And so where it innovates compared to what you have is that you can lift and edit examples from the online help. So there I'm selecting the elastic buckling equation, and I have an example that is lifted straight from the reference manual for the HP50G. And then you see that you have all the values that have been evaluated, and I can change them if I want. What you see, this I equals blah blah blah, is a new kind of object called an assignment, and that stores into value I, and when you evaluate it, it stores but stays in place. And that lets you have on screen a reminder of all the values that were used to initialize your equation, and then you can solve the equation. So you just lift the example from the head directly. That's so you're shifting. You're going through the equation there. You hold the key for the equation to get the help. Then you lift the example here, hit enter. Get this, you edit it the way you want. You enter that, you have all the values, you can edit the individual values if you want. And then when you're done, you select the evaluate at the bottom, and you get the solutions for the system. Now, as you can see, what is interesting is that you have something that is I think, more efficient than even the dedicated application in the HP50G, but it preserves the same user interface that is used everywhere, every other place. So all the benefits that you see with assignment objects and so on are benefits that you can use for anything else, not just equation solving. And so instead of having this sort of special environment that would show your variables and so on, you just use assignment objects on the stack. So this is why these assignment objects are really extremely important to delivering this new kind of RPL integration. So same thing here with another equation. And you see that you edit directly. You have just the command line with your equation here, and you can change which variables you want to solve for. And these are the default units where you want you give an initial value for the search, but the benefit is that it gives you the output unit. So the library itself has grown quite a bit thanks to a guy named Jean Wilson, and it's now 618 equations. That's 96% more than what exists on the HP50G. And 675 variables, that's 70% more than the 396 that exist on the HP50G. And also it has this integrated help that lets you understand, okay, what are all the parameters that I need for this or that equation. So again, credit to Jean Wilson for doing all that work. It's not finished because this pushes the limit of the numerical solver. This pushes the limit of practically every aspect of the RPL implementation. And so Jean has been finding bug after bug after bug. And so I'm still in the process of solving that. Many of the equations that he wants to enter do not work yet just because of limitations in the solver, for instance. The same principle applies to constants. So there is a constants library that is updated and upgraded compared to what exists on the HP50G. And like for equations and library items or units, is easy to extend with an external file. So we have a number of updated constant values. So that doesn't apply too much for basic constants such as pi or e, but if you go to more advanced ones like physics or chemistry constants, you have a complete description of what the constants are and what they mean, including in some cases with graphical explanation, and then you have new values. For each constant, you can see that the menu has two levels, shifted and unshifted, and you have the name of the value, so it's symbolic form, which shows up on the stack in bold, and you have the numerical value, so you shift and a key, and you get directly the numerical value for that constant, including with a unit when a unit applies. The constants that were entered in DB48X have a much improved unit consistency compared to what was done on the HP50G. The main difference here is with respect to angular constants. So anything that has an implicit radians in an equation, for instance, we have explicit angles for all the corresponding constants and equations in the case of DB48X. Now, the philosophy behind this is related to the fact that if you take the arc sign of something, for instance, you're going to get a result that is an actual unit object. Like you could have 30 degrees or pi radians or whatever. As you can see on the screen, there is extensive documentation for all these constants. And that brings us to the next step, which is user-defined libraries. So library objects are simply standard RPL objects that are loaded from the disk. So you load the RPL object from the flash drive, and then you can edit them, etc. The config/library CSV file is where the various objects are indexed, and they can either be defined directly there, so you can load a file using the recall function and the name. So that's what we did just there, and you just simply recall and it loads from the config file. And then we can evaluate these objects directly. But if you evaluate them directly as library objects, then there is a sorry, I should first underline that all the objects in there are in standard RPL syntax. So if we look again at the library.csv file, we're going to look at it and watch on the side that you have a definition, and then you have definitions with equal in the file. And these definitions are for more complicated things that are simply they are stored in their own file. So you have a file for any given object. So when you load the file, it's compiled in memory, and then it's cached, which means that you have a very fast evaluation of all library objects. They are compiled only once, and after that, they evaluate as fast as any object you could have in on the stack. That is actually faster than a global object, because when you look up a global object, you have to scan through memory to find the global object, whereas for library objects, you just have an index somewhere, and so it's accessed much faster. So the library is going to be used to implement a number of utilities and more features. Typically, for instance, we could have a variant of the library that has a number of the things that you would find as sysable values so what is called sys-RPL programming on the HP50G. So all the sys, many of them are really simple things like multiply by 3 or things like that. And we could have a catalog, a library that essentially provides the same thing for compatibility with even sys-RPL level programming. Last step is the performance. So that's the last section of this discussion. the project was really optimized at every single step to run on very small machines. The HP42, the original one, is a tiny, tiny machine. So the design constraints on the HP42 is that we have 700K of program space and 70K of RAM. The benefit is that the HP42 uses the DB48X uses a very low power ARM Cortex M4F chip that runs at 80 MHz. That's relatively slow by modern standards. The benefit is that you get a very high battery life, in theory up to 3 years on one tiny CR2032 battery like this one. So what is the 70K of RAM? That's actually 96K of RAM in the chip. That's 1.5 Commodore 64 for old timers among you. But about 10K are used by the bitmap screen itself, and then the operating system, the stack and so on need a little bit more. There is only 2 megabytes of flash for the firmware, of which only about 700K are free, the rest being taken by the operating system and some utility routines. So, there's 8 megabytes total in the system, but 6 megs are reserved for the flash drive, the flash disk, that appears when you connect the calculator through the USB port. So what is 700K? That's less than what you had on an original Macintosh double-sided floppy disk. That was 800K, so old times. Now this is very, very small, and this means that the DB48X actually hit these constraints quite hard around last Christmas. And essentially we had to redesign and restart from scratch. And that's where the variable precision implementation for floating point was introduced, which takes much less time than the original Intel decimal library. The Intel decimal library was computing on IEEE 754 128-bit decimal binary representation. And it was significantly faster, about 10 times faster at the same precision, but it was of course not variable precision. So how do we actually fit C++ objects in 70K, and how do we make the best use of memory? If you're familiar with the C++ programming language, you'll probably know that an object would be something that looks like an instance of something called a class. So here I have a class called unsigned, and that unsigned class has a private field called value at the bottom, unsigned value. That is the actual data implementation. In memory, this is represented by something called a virtual table pointer that let me do dynamic dispatch on the features inside, like the display function that is marked as virtual, and that means that it's presumably an override of a display feature in the base class, and the vtable lets me select which implementation I use based on the object, on the instance of the object. Now the value, the unsigned value at the bottom needs some space as well, and so my object would have the vtable pointer and then the value itself. But presumably each time I allocate an object, I also need a bit of memory management data, metadata that lets me know what is the size of the object and lets me build a free list of objects for allocation and deallocation and so on. And so this means that my unsigned object on a 32-bit machine like the DB42 CPU would require 3 times 4, and that's 12 bytes of memory. For that price, I can store any number from 0 to about 4 billion, and the object is fixed size, but also because it has this vtable pointer in it and the malloc pointer, I can't move it. So it has to stay at a fixed position in memory. And that is the very reason why doing garbage collection in C++ is hard. So DB48X instead shrinks things and uses a very different approach where the data is not accessed directly through the standard C++ implementation, but instead by using a payload object or a payload member that let me represent a type ID, which is stored with a technique called LEB128, which is an encoding used, for instance, in dwarf, the debugging format that practically everyone uses today. And what LEB128 does is that it stores integers of arbitrary size with the high bit of the last byte of the number is clear and all the others are set. And so this means that any value between 0 and 128 can be stored in 1 byte, and then you need 2 bytes for up to 16,383, and then 3 bytes, and so on. So the type ID is stored using LEB128, and for integers we select a small type ID, so that means we have something that fits in 1 byte. And then the value itself is also coded as LEB128, and if the value is small enough, like the value 1 for instance, also takes 1 byte. And so this means that now I need, for any value below 128, I need only 2 bytes of memory. But because it's variable size, I can have a larger number by having high bit set somewhere after the ID. And so that means that I can store integers that are 0 to infinity. I can have arbitrary precision integers that way. And the object now is variable in size, but more importantly, it can be moved because there is no pointer in it. So I just can copy it around and have the same value. So this means the memory organization is compact, contiguous, and lets me move things around. So in other words, I can have a garbage collector. So the lower part of the memory is a directory of global objects. And the representation is really simple. It's an alternance of an object representing the name, followed by an object representing the value. So for instance, if I have 1 stored in A and hello stored in B, I will have the name A followed by value 1, and the name B followed by the name hello, text hello. And then I have a global pointer that tells me where this ends. Then on top of that, I have temporary objects with the same representation, except that now I have only objects, and they accumulate above the globals. And then above that, I have a scratchpad and the text editor area. And so this representation is contiguous, which means that in order to go to the next object, I compute the size of the current object using its ID, and then I skip to the next one. On the top of the memory, I have what is called root pointers, that are pointers that point somewhere to the objects. And so that includes the stack, local variables, and so on. The xlib entries also are in the high area. So when I have a library object, it's really in the index, I have a root pointer somewhere on the right that points to the computed value somewhere on the left. The root pointers can point inside an object. So for instance, in my temporaries here, I have a list that contains value 1. And the way this is represented is by having the ID for a list with its size, and then I have the objects inside the list. And when I get an object from the list, I simply return the pointer to the object inside the list instead of making a copy. There is also a facility in the firmware for garbage collected safe pointer. So these are smart pointers that will be adjusted by the garbage collector automatically. In the firmware code, they have names that end with _G. So you have, for any type foo, like integer, for instance, you would typically have foo as the object class itself, which is very rarely used directly. Then you have foo_p, that's a naked pointer to it. And then you have foo_g, which is a garbage collected pointer to it. So allocation for these objects is extremely easy and fast. It's one addition and one comparison to see if there is enough free space. So I simply move the scratch pointer like this. And so how does garbage collection works? Well, we simply copy and move objects and we adjust the references. So if I keep allocating objects, at some point memory gets slow, And so we decide that we don't need all these objects and that we want to get rid of them. So these temporaries are no longer needed. And so we move all the objects that are referenced and that we need to keep down. We can then adjust the temporaries in the scratch pad. And now we have some free space. So the benefits of this approach is that there is absolutely no memory overhead. There is not one wasted byte. There is no linked list. There is the root pointers are the only pointers we need to do all that work. So there is not a single wasted byte at the bottom. And pointing to sub-objects does not cost extra. So these two characteristics are the benefits in terms of memory usage. But this means we cannot implement something called a mark and sweep garbage collector, which does require some overhead for each object, and that means we can't deal with sub-objects directly without doing copies. Another benefit of the approach is that the garbage collector is quite simple. It's a single pass, straightforward piece of code. The downside is that it's relatively expensive, since it goes with essentially with both the number of root pointers and the number of objects. Whereas if you do a mark and sweep collector, you can do it in such a way that it grows only in the number of remaining objects. So where does that bring us? We have a small benchmark called the N-Queens benchmark, which is a favorite of the HP Museum. There is a page dedicated to it. And the scale that you see here is actually a logarithmic scale. So this means that the HP15C at the top is several hours, and the HP50G at the bottom is something like a few milliseconds. So this is not a linear scale, again, that's logarithmic. But what you can see is that the DB48X benchmarks on this specific example are among the best. The only one that beats us clearly is the new RPL implementation running on the HP50G for two reasons. The HP50G is actually slightly faster in terms of CPU because new RPL actually boosts the clock for computations. And also, it doesn't use a very, very dense format, the kind I described with DB128 and so on. Instead, it uses direct pointers, which lets it run faster when evaluating objects. But despite that, you can see that DB48X does pretty well, and in particular does better than the stock DM42 firmware, both on USB and on battery. Another important aspect so I highlighted how the encoding of objects is done using DB128 for every piece of data, and that means that RPL is now as compact as keystrokes programs on calculators such as the HP41. And I'll illustrate that with the results from the 2024 handheld calculator programming contest, which was looking for how to generate 24 using the number 7 3 times and the built-in routines of the HP41. Now, the contest was initially targeting the HP41, and you would typically have different targets for RPN and RPL calculators because they don't have exactly the same features and so on. But what I found interesting is that in general, it's expected that RPL would use much more space than what you have on, for instance, an HP41C. There you have a small program that adds 1 and then multiplies by 2, and that would be essentially the core of that program would be something like 4 bytes, or maybe a bit more on an HP41, and it's about 20 bytes on an HP48 calculator. Now with DB48X, that's no longer true, and so you have some comparison here. And what is interesting is that DB48X actually lets me find the smallest of all the results in the competition. It can generate a 9-byte program, where I think the best solution, if I recall correctly, was 11 bytes on the HP41. So this is an interesting comparison point, And you have here a global comparison of all the proposed solutions in the contest, where what you see in green is the DB48X, and the width of the box is the size. So you have each program with the equivalent. So in blue you have the HP48 program, in green you have the DB48X program, and the width is the number of bytes. And so what is interesting is that some programs are wider on DB48X, and there are two reasons for that. Any program that uses arctangent, you need to add one instruction in DB48X, because arctangent gives a unit in DB48X, and you need to strip that unit, so you need to insert a uval to strip it. And the other case is anything that uses statistics, and that's mostly because you can zero add to statistics. So if you add sigma plus, sigma plus, sigma plus, you can do that indefinitely on an HP41, because it has a 4-level stack that is never empty. Whereas if you use the same sigma plus on an RPL system, you end up with an empty stack. So you need to refill the stack, and you need to introduce additional instructions to fill the stack. But the key point is that if you don't have any of these cases, the last one you see here that we just went by, that's the smallest, and it's significantly smaller in DB48X than on the HP41. So this is a validation of the whole approach, because this means we have a machine like the DM42 that has a relatively small amount of memory, and you can really exploit it to do a number of really advanced things. So that's LBLA777. And in fact, so back to the original question, what is DB48X really? So it's not just the best scientific calculator for me. The idea is really to revive Hewlett-Packard's innovative spirit that you saw in all these calculators from the past, and to build a platform where you can have a free software platform where everyone can contribute, we can all build on. And my dream there is not to just go up, but to also go sideways and down with calculators for all kind of use cases with smaller number of features, etc., but would still benefit from all the work done in the user interface to make it easy and consistent and so on. So Steve Jobs, when he was doing a presentation, would always finish his presentations with one more thing. And of course, I need to do the same thing. RPL now does color, and the way it does it is interesting. So there is a variant of DB48X for the iPhone, and that one is in color, and you see some examples here. So the colors are not specifically nice, drawing lines in color here, and so on. So an interesting question is, how do you get portability across gray or black and white RPL and the color version? And the way this was done is that the colors are represented internally as something called a pattern, and that's a 64-bit value always for all platforms. And the RGB and gray commands will generate a 64-bit pattern that depends on the machine you're running on. So it depends on the actual layout of the display. And so that pattern can represent any of an 8 by 8 black and white pattern, and that's the case for the Swiss Macros devices. Or it can be a 4 by 4 16 level of gray pattern, and that's what is going to be used for the HP50G implementation of DB48X if it ever sees the light of day. And for machines that have 16-bit RGB color, it's a 2 by 2 16-bit RGB color pattern. And all this was validated initially on the so there is the very first iteration of DB48X was running on simulators of all three calculators, so the graphic routines are known to work on all three systems. In conclusion, I hope that I could convince you that the better than the best spirit is back, and that we are really trying to build something that is better than any calculator that was done before. I want the user interface to be snappy, to be quick, to be also discoverable, so you can easily find the features you need, and to be consistent. In other words, I really want to take inspiration from the work that was done for the Macintosh on making user interfaces really efficient, but also easy to discover for the average Joe. In terms of computations, I want to have the highest precision pocket calculator bar none, with unlimited precision, exact computations whenever possible, and so on. It's important to have the features that you would get from applications, but through rich and user extensible libraries that really work like the rest of our RPL and interact very well with it. And in terms of performance, the idea was to keep things small, yet to have them faster than any HP calculator that exists today. So now it's time for all of you to get involved. Notably, you can probably contribute a lot regarding the help, regarding even if you don't know how to program, you can read the help files and fix typos in them, or report that you do not understand this or that specific aspect, or add sections in the manual that are missing. But also, if you know anything about C++, then you can get involved in the code itself. Or if you know something about mathematics or physics or whatever, you can help Jean Wilson with the equations library. Thank you very much for your attention. And so in the original Stuttgart presentation, there were questions all along that were extremely interesting, and let me go off a number of tangents. Now, if you have questions about this project, I invite you to put them in comments to this video, and I'll be happy and glad to answer them. Thank you very much, and I hope you enjoyed the video. If you did, please like, share, and subscribe, as usual, to this YouTube channel or to GitHub.